Okay, so we're going to talk about motion. We got a guy. He is moving in what we call a straight line. This is straight line motion. Here's that guy. Clear. Okay. Now, the guy has a position, a location. My guy is located at this position 4. My guy could be located at the origin. That'd be a position of 0. My guy could have a negative position. He could be located here at -3. But what's important about this is that when we talk about motion, we are only talking about a guy moving either to the right or to the left. Okay? That's it. We could also talk about the same situation, but moving up or down. But we're not going to be going diagonally. We don't have to worry about vectors with angles. It's just going to be one direction or the other. The guy can be stationary. He could be moving to the right. See, this velocity has a positive number. That means I'm moving to the right. The guy could be moving to the left. Here he's traveling towards the origin, moving to the left. Notice my velocity is negative. And now he's moving away from the origin, traveling to the left. Here, the velocity is constant. So there's no acceleration, there's no change in velocity, but we could have acceleration, which means he could be speeding up or slowing down, traveling to the left or traveling to the right. Okay? Does this make sense to us? Have we seen position, velocity, and acceleration before on a straight line? Yes. Okay. Now the question becomes, what is the connection with these 3 things to calculus? And you will find this connection very quickly. Before we get to the connection, we're going to talk about like how we are going to list off what's going on. We are going to use x as our function for position, and then it makes sense to use v for velocity and a for acceleration. But we're not going to just say, hey, this guy is located at a position of 2. And hey, he's not moving, he's stationary. We will give it some context. We will be talking about the position at a specific time. If you notice, we have a time meter going on while I was moving our guy. So it's not just like I'm moving him at random, it's like over the course of some time. So it's not just going to be x, we're going to say x of t. So my position is a function of time. At a specific time, I have a specific position. At a specific time, I have a velocity. At a specific time, I have an acceleration. Now let's just say this is at like the beginning, our initial position. Our initial position would be written as x of 0. My position at time 0 is 2. I'm located 2 units to the right of the origin. That's what this number 2 means, a location. Not a direction, just a location. I'm not moving. My velocity, my initial velocity, my velocity at time 0 is 0. But I could be moving to the left at this position or to the right at this position at this specific moment in time. In this situation, we'll keep the position to be at 2, my initial position, but we'd say my velocity would be negative. If I'm moving to the left, should write that down first. My velocity would be some negative number. If I'm moving to the right, my velocity would be some positive number. Okay? All right. Now, let's pretend we got a different guy. We got a guy at time 0 located at position -3. And then at time 2, he is now located at position 5. So let's just write that down just so we have it. X of 0 is -3. X of 2 is 5. Please, with help from your neighbors, discuss how far he's moved, rather how far he's displaced. We don't know what's happening between these two positions. We don't know what's happening at the first second or the first and a half second or the 0.999 second. But we can tell how far he's displaced. And then we could give it some context. We could talk about how far he's displaced or moved over this period of time. So please discuss that with your neighbors. How much has he moved? 8. What's the context of that 8? He's moved 8 meters over.
2 seconds.
Okay.
4 meters.
Okay. All right. So you guys instinctively go straight to he's traveled 8 meters. And the context is that he's traveled those 8 meters over these 2 seconds. And then some of you then said, well, if it's 8 meters over 2 seconds, that's 4 meters per second. And what you just found is what we call an average velocity. On average, if he traveled consistently at 4 meters per second, 4 being a positive number, which means I'm moving to the right. If he moves to the right at 4 meters per second, over 2 seconds, he will cover 8 meters. Now, what you guys didn't think about, and what you probably didn't realize you were doing, is you were doing these calculations. You were saying, I took my ending position, and I subtracted my initial position, and then I divided by my change in my time. Or you did x of 2 minus x of 0 divided by 2 minus 0. You didn't realize you were doing this, but you were. Let me just shrink some stuff here. Okay, well, this formula is familiar to you. You've used this many times before. Discuss with your neighbors. What is that formula? Slope. It's a slope formula. It's a y2 minus a y1. It's an x2 minus an x1. I heard it's an average rate of change. It's a slope of a secant line. I love this. Average rate of change of x gave me an average v. The slope of f of x gave me an average v. Okay, probably want to flip-flop these. Slope of x. Sorry. Slope of x gives me average v. Frustrating. There we go. Slope is the same as the average rate of change of x, gives me an average v. Okay, well, if an average rate of change gives me an average velocity, what do you think would give me, and if just a slope of like a secant or an average rate of change of position gave me an average velocity, what do you think would give me an exact velocity? Yes, an instantaneous rate of change. An instantaneous rate of change of x, or a slope of a tangent. Or a derivative. All three things are the same, right? This is our connection. Little did we know, slopes of position give us velocities. An average rate of change, which is the slope of a secant, gives us an average velocity. An instantaneous rate of change of position gives us an exact velocity. Instantaneous rate of change, another word of saying that is slope of the tangent. Another way of saying both of those is the derivative. So we find that the derivative of position, you think, oh, the derivative of x, x prime? Sure, you're correct, but turns out x prime, that's just v. You are used to f going to f prime. Well, now we have x going to x prime, but turns out x prime is just v. Okay, cool. Don't believe me? Let me show you. In the past, in physics classes, you would be given lots of formulas, right? Physics is all about like using the formulas given to you, it seems like. Right. And you'd give equations like these. These are two equations for projectile motion, throwing objects in the air. You got gravity, which is acceleration, and you'd just be given those. And let's see. This xi, this vi, this a, these are just numbers, right? They are initial conditions, initial position, initial velocity, just numbers, okay? That's a number, that's a number, that's a number, that's just a number, that's just a number. Okay, you'd just be given those. So watch. You didn't have to be given those if you took this class. You could have found this one by taking the derivative of this first one. Let's see.
Physics would have been way easier.
Physics, I'm telling you, would have been way easier if you took calculus first. Yes. Yes. Okay, so let's start with x. Its derivative, dx dt, sure, let's just call it x prime. X prime, okay? X being a variable. But xi is not a variable, it's just a number. What is the derivative of just a number? What's the derivative of 5? 0. Good. I'm glad we don't forget everything. We got 0. Now, we have a number times t. So like 5t or 5x. What's the derivative of 5x? 5. A lot of us, no, not a lot of us made that mistake the first time, okay? The derivative of 5x is just 5. So the derivative of vit, where vi is just a number, is just vi, right? Because like the t will go away, derivative of 5x is 5, derivative of 5t is just 5, derivative of vit, vi. Now, the derivative of 1/2 at squared. 1/2 and a are just numbers. T squared. What is the derivative of t squared? 2t. So 2 times 1/2, gone. A t. 2 times 1/2 at, I just have a t. X prime is the same as v. You see that? They're the exact same. The exact same. You didn't realize it at the time. You thought they were just unrelated to each other, two different equations, but they are very, very, very much related to each other. The slopes of position give us velocities. Okay? Cool. So, let's look at acceleration. We don't just move consistently. So we talked about an average rate of change. Let's say this guy started at a position of -3, and he ended up at a position of 5, but his velocity was not consistently 4. My velocity started at 1 and went to 11. So let's kind of mimic that situation. So, starting at a velocity of 1, getting to a velocity of 11, I'm going to have some of this green stuff going on. I'm going to have to increase my velocity. I'm going to have to speed up. So I'm going to need some acceleration. Has anybody seen that guy before? I think it's just very, very easy to understand motion if you use this guy in a classroom. Okay, so I'm telling you we got a velocity of 1 initially. So here I'd say v of 0 is 1. So more information given that my position is -3. And then my velocity ends up at 11 when I get to this position of 5 after 2 seconds. So my v of 2 ends up being 11. Please tell me the change of v and give me some context. Many of you said, oh, v went up by 10 over 2 seconds. Well, that's a change of 10 meters per second over 2 seconds. That's 5 meters per second squared. What you just found was an average acceleration. What you didn't realize you're doing is using a formula that we've used many times before. A y2 minus a y1 over an x2 minus an x1, or v of 2 minus v of 0 over 2 minus 0. What is this formula? It's slope. It's an average rate of change. The rates of change of v will give us A. Okay? If an average rate of change of V gives us an average A, what do you think would give me an exact A? An instantaneous rate of change. And I don't like to write it, but I should. Gives you exact. You don't have to write exact, it's assumed you're talking about exact if I just put A. So if you pop up here to what we were doing with velocity and position, oh, I wrote exact. Okay, never mind. Okay. Okay? All right. That means instantaneous rate of change, that's a slope of a tangent. Slope of a tangent, a derivative. Derivative of V gives us A. Okay? You can kind of come back up here. You weren't really given an equation ever for A because in this situation, A is just gravity. It's just a constant. If you took the derivative of V prime, you would just get A here. I mean, it's kind of just like, it says it right there with that equation. VI goes away, AT, its derivative is A. Well, guess what? What does that mean, X? What does that mean in relation to X? When we're talking about V prime and A. X double prime is the same as V prime, which is the same as A. The second derivative of position, if you look at the concavity of position, you can tell acceleration. So here's the key. Here's the calculus of motion. It's not really a physics. I should have said the calculus of motion. Slopes give us change, right? Change in X gives us V. Change in V give us A. Or you talk more specifically, the derivative of X. You can think of that as X prime. Well, X prime is just V. The derivative of V, you can think of as V prime. Well, V prime is just A. And v prime is the same as x double prime. This lesson kind of intimidates you when, like, I tell you, like, hey, we're talking about physics. It's like, oh, it's scary. But we have dealt all first semester with f, f prime, and f double prime. And what I'm telling you is that it's the same with motion, only it's x prime, and x double prime. So don't let this scare you. We're just going to be taking derivatives of position, velocity, and acceleration to get information. Okay? It's like what we're going to be doing this unit is the same as we've been doing previous units, at least this first lesson. Same way we've done previous units, just with different context. Okay? Now, I can go the other way. If I have A, I could take the antiderivative. And if I have the antiderivative of A, that'd give you V. The antiderivative of V, that'd give you X. So that's like taking the antiderivative of X double prime to give us X prime to give us X, or F double prime to F prime to F. Okay? We're going to start the first problem so we can get to everything. Now, we are going to be given formulas. It's not like generic formulas we're going to use in all situations, like those projectile formulas, the 1/2 AT squared. It's just going to be like, hey, this specific thing, we typically call them particles, will have a position based on this formula. Okay, so this is the formula for the position of whatever this object is. Okay, and this formula can tell you where this object is located on our number line. Am I at 0? Well, let's think. At 0, I'm starting at 0. By the first second, I'll be at a position -2. X of 1 is -2. So after 1 second, I'm over there. Okay? That makes sense? So, like, you could graph this, and you'd look at it maybe two-dimensionally, but it's still talking about just moving right and left based on where we are in the origin. All right, cool. Now, well, first two questions deal with velocity, average velocity, and what is the velocity? Well, we just need to say right off the bat for both of these questions, the slopes of position give us velocity. Let me just finish these first two. I want an average velocity for the first one. For the second one, though it's not stated, it is implied. If you just are asked what is the velocity, it's implying what is the exact velocity. If you ever ask what is the velocity, they're talking about exact at a moment. Go. So slopes of position give us velocities. We have an average velocity we're asked for. We're asked for a exact velocity. It's not stated, but it's implied. So slopes of secants will give us averages, average rate of change, average velocity. I need to find x of 2. I need to subtract x of 0 divided by 2 minus 0. Plug in 2, 8 minus 12, that's -4. Plug in 0, I get 0. I get -2 in whatever meters per second or something. What you should know is that that value, that average velocity, says on average you're moving left at that rate from 0 to 2 seconds. Marking you late. Be on time after lunch. Okay, so average rate of change position gives us an average velocity. Whenever we're asked to find an exact velocity, well, we know that the instantaneous rate of change of position will give us the instant velocity, or the slope of the tangent, or the derivative of position. X prime, That's v. We will be taking the derivative of x formulas to get x primes, which are v's, and we will be able to plug in values into that. So take the derivative of x, get x prime, plug in 2. You just get 3t squared minus 6t. You plug in 2. V of 2 or x prime of 2 is 0. Okay, so that means we are at rest. That value, velocity, means we are not moving. Okay, so we talked about slopes of position give us velocity. Well, slopes of velocity will give us acceleration. We have 2 questions about acceleration, an average acceleration and an exact acceleration. So just write down that slopes of acceleration, slopes of velocity will give us acceleration. It goes position to velocity to acceleration. Here, the average rate of change of velocity will give us an average v, average a. And then here, the instantaneous rate of change of v will give me an exact a. Okay, so let's start on the top one. Average rate of change of v, I'll just need v of 2 minus v of 0 over 2 minus 0. I've already done a lot of the work. V of 2 is 0. I have v. Let's make sure we recognize what v is. V is 3t squared minus 6t. If I plugged in 0, I also get 0. So I get 0 minus 0 over 2 minus 0. So it looks like my average acceleration is 0. So it looks like I'm just moving constantly to the right, to the left from 0 to 2 seconds at 2 meters per second. We know that's not true. We can see that my velocity at 2 is 0. We will find that if we look at the exact acceleration, that the exact acceleration isn't going to be 0. So instantaneous rate of change of v is exact a. That means the derivative of v which is v prime, which is also x double prime, is a. So f double prime or x double prime will give you an equation for a. We already have v, x's derivative, v's derivative, x's second derivative is 6t minus 6. That comes from the derivative of 3t squared minus 6t. You plug in 2, you get 6. Acceleration talks about the velocity values. My velocity values are going to be increasing from negatives to less negatives, negatives to zeros to positives, positives to more positives. Okay. When does the particle stop? What velocity value are you looking for something that is at rest or stopped? 0. How do you find when something equals 0? You set it equal to 0 to solve, just like we've done so often in the past. Please set your velocity equal to 0 and solve. We should be doing this ourselves. We do not have to copy stuff down, right? We know how to solve 3t squared minus 6t, which is the velocity equation. It gives me my exact velocities. Find out when my velocity equals 0. All right. When something is moving to the left, what are we looking for? Negative what? velocities. Okay. Discuss with your neighbors. How can you determine when velocity is negative? What have we done in the past to determine when things are positive or negative? Discuss. Ms. Chipman, what'd you say? The line thing is correct. The line thing, the sign analysis. That's what it's called. But I'm okay if you said, yeah, you use the line thing. Perfect. Here's my velocity. You know that it could change sign at zeros. You know that in between and outside the zeros, so long as you have all of the zeros, things are going to be consistent. So we just need some test points. We plug in stuff into my velocity function. That's simplified, like 3. Positive times a positive, positive. That means I'm moving to the right when t is greater than 2. From 0 to 2, okay, plug in 1, positive, negative, negative. Here we go, I'm moving to the left. Less than 0. Usually we'll start at 0 and just look at t is greater than or equal to 0. But let's just pretend that we can talk about negative times being in the past. Don't stress about it. -1, negative times a negative, that's a positive. So I'm moving right, then left, then right. I'm moving to the left from 0 to 2. Okay, the next thing that we actually know how to do, because we've taken the first semester of AD calculus, how can we find when something is decreasing? Discuss that with your neighbors. Yes! I like how some people are immediately saying it's the second derivative because you're already thinking of v as being like the first derivative, x prime. And you know to figure out if v is going up or down, you'd have to look at its derivative. And that's kind of what I want us to start at. Velocity is decreasing when its derivative is negative. So that's x's second derivative, or v's first derivative, or a. When a is negative, we will know that velocity is decreasing. So we have to find a. Well, a is v prime. Here's v, find a. And then do a sign analysis of a. A is 6t minus 6. It's just the derivative of v. This is v prime. V prime is just a. It's got a 0 at 1. Plop that 0 down. At 1, you're looking at v prime, which is a, or x double prime. To the right of 1 is positives. To the left of 1 is negatives. Now, I don't want to say like I'm moving right, I'm moving left. It's just like my velocity values are increasing or decreasing. Here my velocity values are decreasing for t's less than 1. Okay, a question that pops up, and you'll see, is asking when is something moving toward the origin? Okay? Let's go back to our guy. It's been 3,600 seconds since we started. Okay. The guy is located, let's say he is over here at a position of 4. He will be moving towards the origin if what is occurring? He's moving to the left, and he's moving to the left when his velocity is. Okay, so does that mean we will say when velocity is negative, I'm moving towards the origin? No, because if his position was negative and he's moving left, he's now moving away from the origin. So if his velocity is negative and his position, there he goes, and his position is positive, you're moving towards the origin. But if he's over here, what does his velocity have to be? Positive. So when you're asked about moving towards or away from the origin, you have to take into account both position and velocity. Now, we've already done a velocity analysis. Here's my velocity. I know I'm moving to the right, then left, and right. You guys need to also do a position analysis. We have not done that yet. Please analyze the signs of your position so you know when you're to the right of the origin and you know when you're to the left of the origin. We have a position function. It was given to us at the top. Please set that equal to 0 and do a sign analysis of your position function. Then, looking at that, as well as your velocity analysis, you should be able to say the intervals in which we are moving towards the origin. Was she coming back? T cubed minus 3t squared is position. Set that equal to 0. Pull out a t squared. T minus 3. I get 3 and 0. So I got position. That could possibly change at 0 and 3. My position is positive, then negative, then negative. It's important to understand what this means. This does not mean I'm moving to the right, moving to the left, moving to the left. This means my location is right of the origin. This negative means my location is left of the origin. Okay? So I got that. And I also have my velocity, which is up here. I'll just throw down here. Please answer the question now. When is my particle moving towards the origin? Okay, answer the question. Check with your neighbors. If I'm left of the origin and moving to the right, there we go. T is less than 0. I'm left of the origin. I'm moving to the right. I'm left of the origin, moving to the right. Am I ever right of the origin, moving left? No. I'd be moving away from the origin from 0 to 2, where I'm already to the left of the origin. And then here, after 3, I'm right of the origin, moving right. So I'd be moving away from the origin. So I'd say t's that are less than 0 and from 2 to 3. Okay? Now, it's important to be able to interpret graphs. Sometimes you'll be given the graph of position. Oftentimes you'll be given the graph of velocity. Just like oftentimes back in Unit 3, you were given the graph of f prime, not the graph of f. Okay? That's okay. You will find that it's very, very similar. It's the same stuff that we've done in the past. We are still doing just with different context. Okay? Now, it's important to be able to interpret this. If this is a position graph, what do these values mean? What does this graph mean? This is time on this x-axis. So at these times, at 2 seconds, I'm at this position. This position is a negative position, which means when my positions are negative, I'm left of the origin. I'm left of 0. If my position is positive, doesn't mean I'm moving up or down. This means I'm right of the origin. We can interpret this to determine whether or not we're moving to the left or to the right. Or, we know rates of change of position give us velocities. If I ask you to sketch a velocity curve, you don't really have to interpret this much. Instead, just look at the slopes of position. Very negative, less negative, less negative, less negative, less negative, less negative, 0 slope. Positive, more positive, less positive, 0. Negative, more negative, more negative, more negative. Right? Those are the slopes of position. That gives me velocities. And it should make sense. If I have a position that's positive, so I'm right of the origin, I then move to get to the origin. Whoops. I move to the left of the origin. I'm moving to the left the entire time until at t equals 2, I've stopped. And I all of a sudden move back towards the origin, which means I'm moving to the right. I get to the origin, I keep moving to the right until I get to a place to the right of the origin where I stop, and then I start moving back to the left. You can sketch that. I've stopped at the second and the 4th second. Negative velocities, positive velocities, negative velocities. Look at that. This is the graph of x prime. That's just v. If you have v and you're looking for a, slopes of v are a. Positive, less positive, less positive, 0. Negative, more negative, more negative. There you go. The next questions you can answer looking at multiple graphs. So just know that. When is the particle stopped? Well, I'll use my highlighter for this in blue. You can either look here, velocity 0, here, velocity 0, or here. I've stopped, my position is constant. Here, my position is constant. I change from going to the left to going to the right. Either way, you get t equals 2 and 4. When I'm going to the right, we can see if you're going to the right, start with a position that's left of the origin, end up with a position that's greater than the origin. You can look at there. Or when is my velocity positive? You can look there. My velocity is positive from 2 to 4. When is my velocity increasing? You can either look at your graph of your velocity, see when it's going up, or velocity is increasing when its derivative is positive. When is v prime positive? That's going to be from 0 to 3. What else could I look at to see when my velocity is increasing? Maybe looking at the x graphs. If you think of V prime or A being x double prime, concavity, oh my goodness, the concavity of x, we're concave up. It's all f, f prime, f double prime. Okay? When are we moving towards the origin? I mean, you could look at the graph of x, it's probably the easiest. I'm moving towards the origin, moving away, moving towards, moving away, moving towards. So 0 to 1, 2 to 3, 4 to 5. Okay? Next question. I'm asking you for a position now. But I don't give you a position function. I'm asking you for a position at t equals 2, but I give you a velocity function. I give you a position at t equals 3. Discuss with your neighbors. What should you do? Don't say just figure it out. If the derivative of position is velocity, then what would you do to velocity to find position? Antiderive. Very good. The antiderivative of velocity will give you position, because this is the same as the antiderivative of x prime. The antiderivative of x prime gives us x. So the antiderivative of v is x. If you keep in mind it goes x to v to a with derivatives, you'll be fine. Then you'll know how to go backwards. So I will take the antiderivative of t squared. And I get what? Oh my goodness, antiderivatives, it's been so long. Very good. Remembering the plus c. It is very, very important, because c could be anything, and we actually really, really need this condition, this x of 3 is equal to 5, so that we can find c, and so that you can find the exact position function. And with that exact position function, you will then find the position at time 2. So please go ahead and finish that. X of 3 is 5. This is just like unit 6. I gave you f prime. Tell me what f of 2 is. If I give you f of 1 is 4. X of 3 is 5. Plug in 3 for t. Set it equal to 5. Plug in 3 for t. Set it equal to 5. I get c is -4. That's not the answer we're looking for. We're looking for the position at time 2. Plug in 2, I get 8/3 minus 4, so that's going to be -4/3. This value tells me a location. I am located to the left of the origin. Tell me, at t equals 2, am I moving towards or away from the origin? Discuss and figure out with your neighbors. Go ahead. Everybody figure it out. I'm going to call on somebody randomly based on who wants to try to get off by not thinking during this second half of this lesson. So, do we have to do the line thingy if I'm only looking at t equals 2? This is very important. I don't need to do a full analysis if I'm just looking at t equals 2. I know my location. Mr. Perrette, I know my location. Now what do I need to know to figure out if I'm going towards or away from the origin? Here's my location at -4/3. Now what do I need to know? My velocity. Is my velocity positive or negative at t equals 2, Mr. Perrette? And tell me the value. You have a formula for velocity. It's given to you in the problem. 4! All right, so what's the answer? We're going towards the origin. We have a negative position of 1 1/3. We have a positive velocity of 4. You press play, you go towards the origin at that moment. Okay? Good. I'm asking you for a position after 5 seconds, and I give you an acceleration. Discuss with your neighbors. What do you have to do? Ready? It's just like if I asked you to give me a value of f, and I gave you f double prime. You'd have to take the antiderivative twice. But each step along the way, you'd have to find c. The antiderivative of a, the antiderivative of 2, that's going to be v. That's 2t plus c. That's f double prime to f prime. We have to find c. Okay, now this is important. If you are told an initial velocity and an initial position, that's my position and my velocity at what time? 0. This is very important. You got to make sure you have this information down because you have to use it. Oops, wrong way. Velocity is 4, position is, velocity is 3, position is 4. So, my velocity at 0 is 3, c is 3. Now I have my velocity function, 2t plus 3. I'll take the antiderivative of velocity to get position. That'll be t squared plus 3t plus a c. X of 0 is 4. C is 4. Plug in 5. $25 plus 15 is 40, plus 4 is 44. Okay? You've done this before. This is not new to you. Okay? You know how to do this stuff. It's just with different context. You may be given the graph of velocity. I gave you the graph of position. Now I'm giving you the graph of velocity. Don't worry, just understand what's given to you. Positive values means you're moving right versus negative values you're moving left. But then understand that acceleration is just slopes of velocities. So the first two questions, easy. You can just look at v. When are we moving to the left between 2 and 4? Easy. When are we stopped? When velocity is 0. The only question that might be tough, when is the acceleration negative? Well, we know if v is like f prime, a is like f double prime. A is the slopes of v. Look at the tangent slopes. Please answer the question and check it with your neighbor. What is the answer to when is the acceleration of the particle negative? Knowing that acceleration is derivatives or slopes of v. What do you think, Mr. Berthume? 1 and 3. Piece of cake. Okay. Here, the tangent slopes are negative. That means the acceleration value is negative. All right, speed. We can also talk about speed. Speed is the absolute value of velocity. It's velocity without direction. If your velocity at a specific time is -2, you'd say your speed is +2. Okay? You typically won't be asked questions of when do we have a certain speed, but you typically will be asked, when are you speeding up? When are you slowing down? When are we speeding up? What do we think? So it's got to have to do with acceleration. And acceleration is going to be what? Positive. Okay, well, here we go. Here's my guy. Here is positive acceleration. I'm speeding up, okay? So now negative acceleration is slowing down. Wait, hold on a second. Hold on. Let's start over. Okay. Positive acceleration, speeding up. Here he comes. He's going to be coming fast. Okay, he's speeding up. Okay. So negative acceleration. Let's start over. Bring him back. Okay, speeding up. So this means must be slowing down. But wait, I'm speeding up. Okay, but now I'm slowing down. Okay, wait, now I'm speeding up. Now I'm slowing down. But now I'm speeding up. So wait, hold on a second. Look at these arrows. I'm speeding up moving to the right, but I can speed up going to the left. I can speed up going to the right. I can speed up going to the left. I can slow down going to the right, speeding up. I can slow down going to the left. So, acceleration positive, not necessarily speeding up. I could have acceleration that's negative and speeding up. Acceleration that is negative, not necessarily slowing down. I'm slowing down there, but I am also slowing down right here. So, looking at those arrows, thinking about those arrows, tell your neighbor, when are we speeding up? Not when acceleration is positive. Love it. When velocity and acceleration are going in the same direction. Since we only worry about right or left, and we only worry about positive and negative signs, same direction is the same as the same sign. If velocity is positive and acceleration is positive, you're speeding up, but you're going to the right. If velocity is negative and acceleration is negative, you're speeding up, but you're going to the left. You're slowing down when your velocity and acceleration are going in opposite directions. Opposite signs. Okay? I give you a position function. I ask you, when is the particle whose position is given by this function? When is the speed of the particle increasing? What do you have to do? Do a sign analysis for V and A. It's like back in Unit 3 when I asked you, hey, when is this function increasing and concave down? You needed to look at both f prime and f double prime at the same time. Now, we've already done this, actually. This was one of our earlier position functions that I gave you. So I'm just going to do the analysis for you, assuming you know what you're doing. We had 0 and 2, and we had 1. We had positive, negatives, positives, and we had positives and negatives. Looking at this sign analysis, which you know how to do, answer, when is the speed increasing? Zero to 1, we're speeding up to the left. 2 to infinity, we're speeding up to the right. I'm going to continue and finish off these notes right now. If you are going because of your off campuses, just please leave quietly. Now, you will be asked to justify and explain answers on your free response test. You'll be asked to explain why you would give this answer. Don't be intimidated by explanations. Why this is the answer is because V and A have the same sign. You could say because V and A are going in the same direction. It doesn't matter. It's that simple. We only have a couple more problems to do. First one is I'm giving you the graph of V. Tell me, if a particle has velocities given here, when is the speed of the particle decreasing, or when are we slowing down? My advice to you, similar to with Unit 3 function analysis, do a sign analysis of V and a sign analysis of A. Knowing that A has what relation to V? Its derivative. Okay, so please do a sign analysis of V and A, and then let's answer this question. Please make sure your sign analysis is the same as mine. And then, after that, check your answers with the neighbor. You're doing speeding up. And you're missing something if you're speeding up. Yeah. When velocity and acceleration are in opposite directions, opposite signs is from 1 to 2, and then 3 to 4. Okay? Now, same question, same type of questions, but I just want to make sure we pay attention to the fact that I'm asking you what is going on at a location. Are we speeding up or slowing down at t equals pi over 9? You do not need a full sign analysis. Just like with that one question I threw in about are we moving towards or away from the origin at t equals 2. I just needed my position and my velocity at 2. Here, to figure out speed, if we're speeding up or slowing down, I'll just need my velocity and my acceleration at t equals pi over 9. Well, they gave me velocity, so might as well use it. Turns into the sine of pi over 3. That's root 3 over 2. I know that's positive. How will I find the sine of A? Take the derivative. V is f prime, it's x prime, A is x double prime. A is the derivative of V. We got to write down what A is correctly. You got to use the chain rule. I don't know if you remember the chain rule. Derivative of the outside, leave the inside alone, times the derivative of the inside, then plug in pi over 9. Turns into cosine of pi over 3 times 3. The cosine of pi over 3 is also positive. So I'm to the right, and my acceleration is positive, which means my velocity is increasing. Going to the right, my speed is increasing. I'm speeding up. V and A have the same sign. Okay. Given x of 0 is 2, is the particle moving towards or away from the origin at t equals pi over 9? It's a great question. So I'll need, first of all, v of pi over 9. I know v of pi over 9 is positive. So I know I'm moving to the right. But now I have to find x. Which means I need to take the antiderivative of v, because you were not given x, you were given v. V is sine of 3t. What is the antiderivative of sine 3t? Oh, phenomenal. Excellent job, guys. We know that cosine's derivative is negative sine, so I need a negative cosine. But we remember, since I have a coefficient of a variable, when you go backwards, you need a reciprocal of the coefficient of the variable. Don't forget a plus c. X of 0 is 2. Okay, so x of 0, that's negative 1/3 cosine 0. Plus I add 1/3 to 2, that's 7/3. I have my function for x, negative 1/3 cosine 3t plus 7/3. I plug in pi over 9 to find my position. Cosine of pi over 3 is 1/2. So I got negative 1/3 times 1/2 plus 7/3. My particle is to the right of the origin. My particle is moving right, so I'm moving away. X of pi over 9 is positive. V of pi over 9 is positive. I'm right, moving right, I'm moving away. Okay? I hope we are not intimidated by this stuff. I hope we see that it's really just like a review of everything we did in the first semester, just with x, v, and a instead of f prime, f double prime. And that's the purpose of this being the first lesson of the second semester, just to review and get back into the swing of things.